So why bother measuring biodiversity? What do we mean? What's different about measuring biodiversity than just throwing a quadrat? Well, the actual measurement of biodiversity is very important to overcome the subjectivity that ecologists often face when looking at grasslands. So here we've got a garden, so we've got typical grass, but I know that this part of the garden up here has much older grassland than down here, which is relatively new. So when looking at the garden, you say, well, I think one part of the garden is more diverse than the other. And somebody else comes along and says, oh, I don't agree with you. I think this part up here is less diverse than this one down here. And so you look a bit more carefully, and you can see here this particular photograph is of this part of the garden. In fact, you can see there's a buttercup down there and a few other odds and ends there, and some daisies too up here. And this bit is just really a bit of moss, a few blades of grass and a few little herbs there, some speed oil coming through. And this one here is taken at the top, and this one here is taken down below. Now, what can we do then? What can we do to make it objective? So this is the formula we use to calculate diversity in an objective way. So this is the Simpson's index, and the D right at the start here, that D stands for, as you can guess, stands for diversity. And we've got a number of different symbols in here, which we'll come to in a moment. But what's important about this Simpson's index is that it takes into account species richness, which is the number of different species present in the area, but also takes into account the species evenness. And species evenness is the number of individuals of one species that are present in that area. So looking back then at this little equation, we've got little n, we've got big N, and then we've got this E-shaped symbol. Now the little n in the formula stands for the total number of organisms of one species. The big N is the total number of organisms, and the little funny shaped thing, that, as I'm sure many of you already know, is the sum of. So what we've got then is the sum of little n, the total number of organisms in one species, divided by the big N, which is the total number of all organisms, and then you square that, so you divide little n by big N, and then you square it, and then you add them together. And once you've added them together, then what you have to do is you have to take them away from the one that's here right at the start. So whatever answer you get in here, you have to take away from 1, and you end up with a number that is smaller than 1. So we have our result, and you're always going to get a value between 0 and 1. And this value between 0 and 1 tells you something very important. If it's a high value, it's closer to 1, it's more diverse. If it's a low value, closer to 0, then it is less diverse. Now, the important thing is, the more diverse an environment is, then it's more stable. So it can cope with change really quite easily. If something, though, is less diverse, it's less stable, and so it's easily damaged by change. So this formula here, once you've worked it out, tells you if your environment is diverse and stable, or not very diverse and less stable. So imagine, here we are, we've gone on a field trip. Remember field trips, excursions, when we could go out and do things. So anyway, here we all are, imagine yourselves there, and we take with us some quadrats, some tapes, buckets, white trays, and we lay a tape down and we do a transect. And every so often, say every 2 meters, we'd put our quadrat down and we would record the number of individuals of each different species that we could find. So imagine we put down our first quadrat, so here's our record sheet, And so our first quadrat 1, say we found some sea anemones. Very lucky, found one sea anemone in our first quadrat, so here's a sea anemone, and we put a number 1 there. And we would go and we'd explore, and there we have some dog whelks. Now we look at our record sheet, there's no dog whelks listed, so we would have to add the dog whelk to our list. So we would pop it in just underneath where we've got our space for the top shell. Then we would continue to do that. We'd be looking in all our different quadrats along our route, recording all the different species that we find, counting them, and so gradually filling in all the gaps with all the different species that we find, and recording the individual numbers in the columns as we go along. And so by the end of it, we'd have 10 quadrats, lots of data, and get some idea of the numbers of different species and the numbers of individuals in our rocky shore. And then what we would do is we would go round the corner of the cliff, and we would go to the next bay, and we would do exactly the same thing again on another piece of rocky shore, filling in another worksheet. So we'd have 2 sets of data, and we could work out the Simpson's index diversity for site A and for site B. So here we are with our data. So we went to 2 sites. We went to site A and site B, and in site A we recorded all the different species that we could find, and we did the same in site B. And what we've done is we've taken all the data that was on the 2 record sheets and we put them into one table. So we've got shore A, shore B, all the species lists down here. Remember, number of individuals in the formula up here is the little n. Little n represents the number of individuals. So what you can see from our 10 quadrats, we had 367 limpets in shore A, we had 125 in shore B, and so on with all the different numbers and comparisons at the 2 different sites. Giving us a total in shore A, adding them all up, we get 1,107. Do the same for shore B, add them all up, and we get a total of 861 individuals sampled and counted and recorded. So what do we do next? Here's our second table, and you can see we've now got for shore A, just one table for shore A, species list down the side, the n number, so the individual number that we counted, so this is the same as this column here. And then what we do is we divide little n, number of individuals, by big N. And big N, as you can see here, is the total number of individuals. So that's our 1,107. So all you do then is you divide little n by big N, and you get this number, and then you square it. And you do the same for each one, and you square each one individually, and then you add them all up. So you end up with the total, this symbol here, of 0.201. And don't forget the next step, because back up here you can see that D is equal to 1 minus your calculation. So you mustn't forget that step. So we take 1 here and take away the 0.201, and we get 0.799. So 0.799 is very close to 1. So this means that this area is quite diverse. But let's compare it now to shore B. So maybe pause the video for a minute and have a look at the table. Do you think shore B is going to be more diverse or less diverse? Remember, the Simpson's index allows you to compare species richness and species evenness. So look at the numbers. What do you think shore B will come out as? More diverse or less diverse? So looking at shore B, exactly the same table, exactly the same principle here. Divide one by the other. So in this case, we're dividing 51 by 861. We're getting 0.059, which we square to get 0.004. Repeat, add them up together, you get the sum of 0.267. And as I say, keep saying, do not forget this step here, take 0.267 away from 1, and then you will get the answer of 0.733. Now you'll see that this, you may remember, this is now a little bit less than shore A. And it's probably due to this, our snake lock anemones, and we didn't have any on shore B. So overall then, what we've done is we can compared site A with site B, and site A, even though it looks quite similar to site B, has in fact got a slightly higher Simpson's index of 0.799 compared to the Simpson's index of site B of 0.733. Hello, and I hope that was helpful, and I hope you're all okay. Bye!